All right, so I'm making this video to go over the basic probabilities that are associated with viruses or diseases. This works for pretty much anything, but just to make sure that everyone's kind of on the same page here, we're we don't have to be statisticians, but hopefully this video will help just ease some, make some information easier to process. So let's just say we have disease A. With a fatality rate of 10%. Now, in the probability and statistics world, we like to keep our numbers between 0 and 1. Where 1 represents 100%, 0 is 0%. So a 10% fatality rate we would write as P of F, which is the probability of a fatality, where F represents a fatality. We'll say that's equal to 0.1. So that's 10%. And so let's look at this a little bit further. What if we have N in green here is the number of cases of people with this disease, this virus, this infection, or whatever. And NF is the number of fatalities that end up happening of those N cases. Now, we can talk about probabilities, but first, how many numbers of people do we actually expect to die given some probability of fatality and some number of cases? And so the naive approach might just be to multiply those two things together. Say, well, if you have 10 people with the case N and they have a 10% chance of dying, then the number of people to die should be about 1. That's not exactly true. So that is what we call the expected number of fatalities, E of NF. So that is in a, if you have hundreds of thousands of cases of this, and you can do this, and overall that'd be pretty close to what we expect. In small sample sizes, we rarely get the expected number. It's like flipping a coin, right? Even though if it's a fair coin, you have a 50% chance of heads or tails, you can easily flip it 5 times and get 5 heads, right? It's not impossible. It's not the most likely thing, but it could happen. But we only expect, well, out of 5 times, you expect 2.5 heads, 2.5 tails, which can't even happen anyway. So that tells you what you need to know about this type of approach. It's not exactly useful for telling you what exactly is going to happen, but it is useful for having an expectation of what might happen. So what if someone asks you, what are the chances of seeing NF right here, where NF is the number of fatalities, deaths, given N cases? And so your goal here is, how fatal this disease is in probability world. It's got 10% fatality rate. We know how many people are infected with it. So what are the chances of seeing different numbers of people dying from it? It's kind of complicated to look into it, and let's talk about why. So given 5 people in this example right here, we've got 5 dudes right here. Each of them has a probability of fatality of about 0.1, or exactly 0.1. And each of them, because of that, since a disease, we're going to say, can only allow someone to die or recover from it, then the opposite scenario is that they recover, which is probability of recovery here, R for recovery, is 0.9. So in this scenario, each person has a 0.1 probability of succumbing to the disease and 0.9 chance of recovering. So how many of these guys are actually going to die? And so if you did their expected approach right here, this is just N times P of F, well, N is 5. And P of F is 0.1. So if you just multiply those together, you get 0.5. So it's expected that half of a person will die out of these 5 people from this virus. Obviously, that's not a realistic thing. That can't happen, right? In our scenario, we can either die or we can't die. We're not going to have half a person die. So already we know we can't just multiply our probability by the number of people and then get the people who will actually die. That just gives us an expectation. On average, if you had thousands of samples of these 5 people, on average, half a person out of those 5 will die, right? So, but of course, in many of those cases, all 5 could die, right? Even if it's 10% chance, that's still very possible. Or no one can die. That's even more likely, right? None of these guys will die. And so we don't really know what's going to happen deterministically. We just have kind of, it's a random sample. It's a random trial. Anything can happen. But we have some information. Do we want to compete, though? What are the likelihoods of these things happening? So let's take a look at that. Let's talk about the scenarios where 1 of the 5 dies. All right, 1 person out of the 5 unfortunately succumbs to the disease. So NF is equal to 1 here. In these cases, we've got these 5 different scenarios I've put together. In the first scenario, the first guy dies, but the other 4 recover. In the second scenario, the first guy also recovers. The second guy dies, and the other 3 recover. And so on and so forth. You can see these are the different ways. These are all the possible ways that from these 5 people, these 5 unique individuals, that one of them would die. These are the different ways it could happen. The probability of this first one happening is basically, it's this simple formula. So we're considering someone dying or surviving to be independent from a different person dying or surviving from the the disease. So the first guy, he died, unfortunately. So he had a 0.1, there was a 0.1 probability of that happening. But the other guys all recovered. And so each of them, they recovered, and recovering has a 0.9 probability. And so we multiply all those together, and we come out with this answer right here, 0.1 times 0.9 to the 4. The exact answer isn't really relevant right now. We can kind of see some information, though, some sort of generic generalizations we might be able to make from here, where one person died, and that's their probability. And not 4 people recovered, and this is the total probability of that happening. But this is just for this one case. The second case, second scenario, also has that same probability of happening. And so does the third, and so does the fourth, and so does the fifth. So all these scenarios are equally likely, right? And we basically have 5 different ways this could happen where one person dies. Each of them has a certain probability. So what's the total probability out of all different scenarios that one person dies? Right? We want to know now the probability of any of these happening. We don't care that if it was this first scenario or the third scenario. We don't care which one of them is the one who dies, but we just want to know what are the odds of one person dying. And so what we do is we'll take the probabilities from all the different scenarios and we'll add them together, right? Because it's basically, we're saying, what's the chance that one person dies? Well, that's a chance that one person dies in this first way, plus the chance that the one person dies in the second way and the third way. And so we add them together. Since they're all the same number, each of the probabilities for each of the scenarios, we can just multiply that number by 5. So we get 5 times 0.1 times 0.9 to the 4. That's the total probability of one person out of 5 dying. If you have 5 people with the disease and the 0.1% chance, 0.1 probability of dying from the disease. This comes out to 0.328. So around 32.8, 33, so basically a third of the time that you have 5 people with this disease, exactly one of them will die, right? It doesn't matter which one, but that's the chances that the probability that one person dies out of the 5 infected, 33% of the time. Note, this is not, again, equal to just n times P of f, which would give us half a person, right? Half a person didn't die here. We didn't get a 50% chance. It's just weird, right? It doesn't work that way. We've got this equation here, and so we've talked about what are the scenarios where one person dies. But what if we want to know, okay, what are the odds that 2 people will die out of this 5? Well, can we generalize this equation here? Is this a generic formula that we can use for other values of NF? Sort of. Let's take a look at what we did here. We've got 5, right? We've got 0.1. Oh, we know what that is. That's a probability of f. But we know that it was only 0.1 to the 1th power because only one person died. So we can put NF in that exponent. And we've got 0.9 to the 4. Well, 0.9 is a probability of recovery, and 4 is not 1 minus NF. That's a mistake here. Let me go ahead and just fix that really quickly. This should be... Oh, this came out terrible. 1 second. Let's make this nice and fat. N minus NF. So N again was 5. NF is equal to 1. And so this equals 4, right? So 0.9 to the 4. Again, this is a mistake here. This is N. All right. So probability P of R is also equal to 1 minus P of F. So you're going to use either there. So we've got this separate formula, but what is this 5? You know, is this 5 because we have 5 people? Or is this 5 because we have 5 scenarios under which that one person might die? And that's what it is. It's the number of ways that one person might die. So let's try to generalize this a little bit further. Can we make a formula out of this? Yeah, it turns out the 5 comes from the total number of ways you can have one death out of 5 cases. But if you have a different number of deaths, there are not 5 ways to do so, right? So if we said, okay, what are the chances that 2 out of the 5 people die? There's not 5 different ways that those 2 people will die. For example, let's take a look at the scenario, exactly as I just mentioned, where 2 out of 5 die, where NF equals 2. So here it's going to be a little bit longer, but these are 10 unique ways under which 2 people might die. So for example, in the first scenario, the first 2 die, 3 recover. In the next scenario, the first guy and the third guy dies, and everyone else recovers. And then so on and so forth. You'll see how we have all these unique ways, and none of these are repeated. So all of these are 10 different ways under which 2 total people die, 3 recover. So it's 10 ways for 2 out of 5 to die. And over here, it was 5 ways for 1 out of 5 to die. So is this just like 2 times 5 for this case and 1 times 5 for the other case? So is it just n times nf is the number of ways to do this? right? After all, 5 ways for one of 5 to die, and the answer, unfortunately, is no. So, for example, just to prove why, you just look at the 0 out of 5 case. In this case, no one dies, but there's one way for this to happen. It's not 0 times 5. That'd be 0. There'd be 0 ways for this to happen. It's 1, which wouldn't work from this formula, right? So the formula is not generic enough. There's got to be some other way to figure out the number of ways that a certain amount of people out of a certain group will die. The solution is called the binomial coefficient. And I know it looks ugly. I always forget what the formula is. I always have to go to Wikipedia to look it up. But basically, it's represented by this n over k in this like parentheses. And it breaks down to this. N factorial over k factorial times, n factorial divided by k factorial times n minus k factorial. If you don't know what a factorial is, that's the exclamation mark. Basically, 3 factorial is 3 times 2 times 1. So it's basically starting from that number, multiplied by all the previous numbers until you get to 1. So 3 factorial is 3 times 2 by 1 times 1. That gives you 6. 0 factorial is a special case. That's just defined as 1. It's not 0. And that's also the same as 1 factorial, which is just 1. So 0 and 1 factorial are both 1. All right. So this binomial coefficient, what does it mean? Given in the combinatrix or whatever, it's basically given n choices, you can choose k of them, n over k, different ways. So if you have n choices and you want to choose k of those choices, you have this value, this n factorial over k factorial, n minus k factorial, different ways you can do that. All right. So in our scenario, we're saying we have 5 choices, n is equal to 5. K is the number of fatalities we want to look at. So if we have 5 people, how many different ways can you have k equals 1 of them die? And same thing with nf equals 2, 3, and 4. So let's look at some of those examples. Nf is equal to 0. So we have 5 people, and we want to choose 0 of them. How many different ways can we do that? It's 5 over 0 in the notation, which breaks down to 5 factorial over 0 factorial, 5 minus 0 factorial. Remember, 0 factorial is defined as 1, so that's just a 1. So it's multiplication, you can just ignore it. 5 factorial, 5 minus 0 is 5. So just 5 factorial over 5 factorial, which is 1, right? Any number divided by itself is 1. You don't even have to care about how this is computed. So 1 total ways. And that jives with our analysis right here, right? We have 0 people dying out of the 5 cases. And so there's only one way that this would happen, and this equation gives it to you. What about the 1 person out of 5 dies? You do 5 over 1 in the binomial coefficient, and that breaks down to 5 factorial over 1 factorial, 5 minus 1 factorial. Again, 1 factorial is equal to 1, and you can just ignore it. So we got 5 factorial over 5 minus 4. 5 minus 1 is 4, and that's factorial. So that's 5 factorial over 4 factorial. The secret to this equation here, like, oh man, do you have to do 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 3 times 2 times 1? No, you can just kind of cheat. And so the cheat here is that 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And 4 factorial in the denominator is equal to 4 times 3 times 2 times 1. And so if you divided these two numbers, you notice that all these pairs would cancel out. And so it's just equal to 5. So that's just the shortcut. You don't have to compute all the numbers. Well, anyway, this thing right here says that if you have 5 people and you have to choose the number of ways that one of them would die, there's 5 different ways to do that. And once again, if we bring it all the way back, that's where we've got this originally, right? If you have 5 people and one of them dies, we have 5 different ways for this to happen. 1, 2, 3, 4, 5. And you can do this for all the other ones. If you do it for 5, 2, you'll see that the answer is 10, so on and so forth. All right. So our end result is this. We've got the number of people that this right here in this binomial coefficient will tell us, hey, given n people, how many different ways is nf, can you choose nf from them? So the probability of nf people dying, given n cases, is given by this equation right here. It's the probability of nf, which is number of fatalities. This bar means given n. So given n cases is equal to the number of ways you can pick those nf people out of n times the probability of f, right? Oh man, I think I made a mistake here. This should be, I didn't make much of a mistake. I just need to add one more thing here. Let's go ahead and make this a little small. This should be raised to the nf power. So it's a number of different ways you can do it, times the probability of fatalities to the power that you want to raise it to. So how many fatalities you're looking for, times the opposite of that happening, 1 minus p of f, to the remaining power, right? So remember, if n is 5, nf is 1, then this becomes 1, and this becomes 4. So 1 and 4 give you 5. If n was 5 and nf was 4, so there's 4 people who would die, this becomes 4 over here, and n, 5 minus 4 becomes 1. Again, 4 and 1 is 5. So there's always a total number of 5 of this term plus this term. They have to, be the total different scenarios for those n people. But this right here will give you the probability for any given arbitrary number of cases, arbitrary number of fatalities from those cases, and arbitrary fatality rates, P of F. So you can just go and plug and chug and go wild with this equation. So yeah, I don't really know why I made this video. It took a lot of work for some reason, so hopefully it's useful. Thanks.